really going on. What is the introduction? We're going to look into that. So in this session, we're going to see how we can build neural networks which are capable of learning the complex kinds of relationship deep neural networks which are famous for. So the key idea here is obviously modularity, building very complex and high level network for using simple function units, and for the representation purposes we'll be using initially linear functions to represent it. What is neural network? So there is a simple definition given by Dr. Robert Hecht Nielsen: a computing system made up of a number of simple, highly interconnected processing elements which process information by the dynamic state response to external output. It's nothing but getting all these inputs. It's going to apply activation function and determine which feature can light up that particular problem statement or so and give us the output. So I'll explain briefly in a moment the basics of neural network. So they are typically organized in layers. So as you can see, which are made up of number of interconnected nodes, and each node contains the output value and the activation function on which it works upon. Patterns are represented to the network via input layer, which communicates to one or more hidden layers. So each node communicates to all the different nodes in the dense layer or the hidden layer, each layers. So there going to be weight and biases applied to each of those layers, and we'll see what it does and how we can explain this in a moment. So neural networks are also called as feed-forward neural networks, and they're also known as artificial neural networks. So layers. Neural networks typically organize the neurons into layers, as I said. So right now, when we collect together linear units having a common set of inputs, we get a dense layer. So this is known as a dense layer. So these are the input features that we're going to supply the neural network, or put these features into the neural network. So this could be anything that the features that you're going to put into the neural network, and this dense layer is going to act upon all these input features and get some value, and it's going to output them. So that's what I have explained here: a dense layer of two linear units receiving two inputs and a bias. So bias is this one you can see here is nothing but a bias. So we have two input features and a bias. So bias is nothing but it boosts the weighted and bias values for these two features. So bias is nothing but you can specify it like a regulator, some sort of regulator and booster. Bias is nothing but that. You could think of each layer in a neural network as performing some kind of relatively simple transformation. So through a deep stack of layers, a neural network can transform its inputs in more and more complex ways. Not only that, not only one layer, you can add many hidden layers also. So the hidden layer in this context is a layer in Keras is a very general kind of thing. Layer can be essentially any kind of data transformation, and you can add many layers as many as you want. So there is no constant like blueprint that you have to add this many layers and you have to have these many neurons or such. There's no such thing. This is just this visual representation you see, this image you see is just basic architecture of a basic neural network. So what's happening here is we have three input features. I have not initialized the biases here. It's kind of given, and these three input feature is all connected to these four nodes. So this node you can see here is connected to each and every node of this hidden layer, and as such of these next two input features also. So each node and each vector we can represent as that, or we can call them as vectors, holds a weight. So each node holds different types of weights, and these weights represent the answer for that particular problem, and this is transformed into the output layer. So it's kind of hard to get track these type of information, so we'll visualize them completely in the next phase. So this is just for theory purposes. A neural network is basically a sequence of operations applied to a matrix of input data. So you can see why do we have to use neural network other than using machine learning algorithms for this. So machine learning algorithms is basically for numerical problems. You can use deep neural networks for numerical problems also, but it's better to use machine learning because deep learning can handle way more complex data, and it has a lot of other uses. So the important functionality of neural network, why it is superior to machine learning algorithms, is called propagation. There's an important trick with neural network which is called back propagation. It is a procedure that allows us to update the model variables based on the learning rate and the output of the loss function. It's nothing but we are relearning the entire model based on the output which the model predicted. So it's feeding back the same output, and it's adjusting towards the weight that it wants the output to classify it as. So that's what back propagation really does, and it's an algorithm for supervised learning. So we can use back propagation for supervised learning of artificial neural networks. That's what I said, using gradient descent. So gradient descent is the basic optimizer algorithm that we're going to be using for neural networks. Given an artificial neural network and an error function, the method calculates the gradient of the error function with respect to the neural network's weights. So that's all about back propagation, and this is more like a mathematical representation of how a neural network works between layers. Perceptron formula is nothing but this formula we get. This is nothing but the summation of all the weights that these features is going to represent about this node, and this node, after getting all those important weights, is going to apply some activation function. So activation function in this case is like a stepwise activation function. So you might have heard sigmoid, right? Sigmoid, linear activation function, and ReLU, tanh. So these are all activation function to help the model side with the graph that we're going to represent. Activation function helps the model to output the important variables. So this is what like structures the model. You can apply any activation function depending upon the model. If it's a binary classification, it's sigmoid, or linear classification, you can use linear or ReLU or tanh, some sort of stuff. So next, that comes on to the next phase, which is called activation function. What is activation function? It turns out that two dense layers with nothing in between are no better than single dense layer by itself. So if you don't supply an activation function to a neural network, it's nothing but a machine learning algorithm that's going to learn without any guidance. So activation function is very important in neural network. So that defines the model. So what activation function you're giving it to the model, it defines the output and it defines the prediction of your model. It shapes your model. So next thing, most important thing, like I said, without activation functions, neural networks can only learn linear relationship in order to fit curves. So your data is not always structured, as I said earlier. It does not always follow a linear pattern. So our data is going to be unstructured and it's going to follow a lot of curves, and in order to fit this type of data, you need to fit the data accordingly. So sometimes the data might be curved. So in order to fit these curves, we need to use activation functions. So activation functions help us a lot in shaping the data. So this is nothing but a representation, a non-linear relationship. This is what this data is. As you can see clearly, it is non-linear, right? You have curves here. So when you apply activation function, this is what you get, this curve. So our model has fit the data perfectly. If you don't apply activation function, it's going to be a straight line in between them. So the error is going to be large, variance will be high. Rectifier function. So rectifier function, or ReLU, is the most basic and famous algorithm or function, activation function, that everyone uses in their neural networks. A ReLU function is very simple and is optimized, and it doesn't generalize. It doesn't like be aggressive towards outliers, and it generalizes perfectly. And another important feature of ReLU is that if you don't know what activation function to use for your neural network model, you can always go and choose ReLU. So rectifier function has a graph that's a line with a negative part. So what it does is that if anything lies below, if any data which is a negative or lies below 0, it's going to classify it as 0, and anything above 0 is going to follow the graph. So nothing but we are taking the max between the two values, and it's muting out the negative or the values below 0. So when we attach the rectifier to a linear unit, we get a rectified linear unit, or ReLU. So this is weight into x plus b is nothing but y is equal to ms plus b, linear equation, and w is the slope. W is the slope here, obviously, and we can apply that and get the max between them to get the ReLU function. So ReLU function does the job, and these are the type of activation functions that we'll be using in neural network. Sine, unit step, linear. So This is more like trial and error, and based on the model, you can use these activation functions. This is the 1D graph. And next step, stacking dense layers. So as I said earlier, not one hidden layer can be used to build neural network models. You can use a lot of different hidden layers and a lot of hidden layers and different hidden neurons also. There is no constant blueprint that you must follow for this. It's free to you. You can use how many you want, but you should also keep in mind the overfitting problem. So this is how a neural network architecture looks like for a neural network which has different hidden layers. The layers before the output are sometimes called as hidden since we never see their outputs directly. So because we will only see the outputs for this linear module, and we don't see the outputs for these hidden layers or these neurons or these layers. Hence the term hidden, because this all happens in the background. And we move on to the next step, building sequential models. So what I did here is I haven't used any specific data for this. This is just a syntax to get you understand and to get you working on how we can build a neural network, importing this library, which Keras library, which is offered by TensorFlow. And TensorFlow is nothing but deep learning library. You might have all been familiar with TensorFlow, and Keras is nothing but the wrapper to make the code even easier. The wrapper is around TensorFlow naturally. So I imported Keras from TensorFlow and also layers. So this is how you're going to be building the model. So this is the model architecture or the structure. These two are the hidden layers. Layers.dense. Units is equal to 4 is nothing but the nodes, number of nodes or number of neurons you're going to have in that particular layer. Activation ReLU. Input shape. So yeah, you have to specify the input shape because the features is going to be flattened and fed to the model, and you have to specify that input shape. And this is another hit. We're going to add another hidden layer which has 3 neurons, and ReLU as the activation function. And output layer is going to have just 1 neuron because we're going to have output just 1 variable. And this is just a basic statement or syntax that we use to build sequential models. Deep learning model lifecycle. So in this section, you will discover the life cycle for a deep learning model and the two Keras APIs that you can use to define the models. So every time when you build a neural network model or a deep learning model, you have to follow this life cycle. There are 5 steps you need to follow while building a model. Those 5 steps are: first, you have to define the model. Second, you have to compile the model in order for it to run. Third, fit the model to the particular data that you want to train. And after it fitted the model, you have to evaluate the model's performance, whether it's doing good or bad. And after that, after evaluating your model, you can make your prediction. So this is the life cycle of a deep learning model. This is the steps you're going to follow, and these are the steps that we're going to follow in this session. So let me walk you through the basic and brief steps of each of these sections one by one. Defining the model. Defining the model requires that you first select the type of model that you need and then choose the architecture and network topology. So after looking at the data, you have to specify the type of model that you want and really brainstorm the ideas and whether to use mini neural networks or hidden, and according to the type of data, you have to build the architecture. You have to define the model. So sequential API is being used for building these purposes model. Second step, compiling the model. Compiling the model requires that you first select a loss function. So in the compiling section, we'll be specifying what optimizer that we'll be needing, what loss function that will be supplying the model with and evaluating the model. And usually the loss function will be mean squared error or binary cross entropy or categorical cross entropy. So that sort of stuff. And optimizer. Optimizer is nothing but the optimization algorithm with which the neural network will reduce the cost upon. Usually you have heard about the gradient descent, right? Gradient descent is type of optimizer algorithm, and there are a lot of different algorithms we have. Yeah, a lot of different optimization algorithms we have, like stochastic gradient descent or ADAM or ADAGRAD or RMS prop, and these are the type of optimizers that you can use for your particular neural network model. So when to use which which activation when to use which activation function and which optimizer. So as I said, there are a lot of optimizers: SGD, RMS prop, Adam, Adagrad, and Delta. So let's visualize what each of those optimization algorithms does on a contour plot. So contour plot is nothing but the depth, and the star you see is nothing but the lowest global minimum of that particular graph. So global minimum is nothing but the lowest amount of cost that each optimization algorithm can reach, and the time. So it represents the time. So you can see clearly that SGD is better, and Adam is also better. Adam generalizes better. Ada delta is like a little bit fast, and Ada grad is very slow. So it gives you an idea between what optimizers that you can use for a particular neural network model. This is like a comparison between the iterations and the loss. RMS prop like converged way sooner. The RMS prop converged at the local global minimum way sooner than the other optimizers, but it has like a lot of, it loses outliers and it doesn't generalize better with the model. So the best algorithm that we always use and data scientists always use and other companies also use is that Adam optimizer. Adam optimizer is the first go-to optimizers that everyone uses. So I would also suggest you to use that Adam optimizer. You can see the yellow line. It does take some time to converge, but it does the job. Adam optimizer algorithm is an extension to the stochastic gradient descent. Adam is an optimization algorithm that can be used instead of the classical stochastic gradient descent procedure to update the network weights based on the training data. How does Adam work? Adam is nothing but a combination of Adagrad and RMS prop. So Adam has basically the advantages of both RMS prop and Adagrad. So these both algorithms, optimization algorithms combined, brings us the Adam. So that's why Adam is very famous and quite popularly used optimizer in artificial intelligence world. Now let's see how we can like compile and how we can specify optimization for each particular neural network. So we're going to create a variable opt and use optimizer. In this case, SGD. You can define SGD optimizer using this syntax. Learning rate you have to specify. Learning rate is nothing but the number of steps you're going to take, and momentum is the speed. And this is how you can compile a model. So I have no data right now because for this is just the syntax purposes. I have like used a demo model, a dummy model. And three of the most common loss functions are like, instead of mean squared error, we'll be using binary cross entropy for binary classification problems, sparse categorical cross entropy for multi-class classifications, and you can use MAE or MSE for regression. And this is how you compile a deep learning model after you created the architecture. So you're going to specify the model and compile them, specify the optimizer that you want to be used. We have used that OPT variable here, which holds the optimizer stochastic gradient descent, and the loss function. We're going to assume the problem has binary classification, and we're going to specify binary cross entropy for this. And metrics is nothing but based on what you're going to evaluate this model. So we're going to evaluate this model on accuracy. So after compiling, you have to fit the model, right, to the data. So the fitting the model requires that you first select the training configuration, such as the number of epochs. So epochs is nothing but the number of loops the model is going to take a look at the training set. So if you specify 5 epochs, it's going to take a look at the model 5 times. It's going to train the model by looking at the data 5 times. And the batch size is nothing but the number of samples in an epoch used to estimate model error. So this is the basic idea, and this is the syntax that we use to fit the deep learning model. So after compiling, we're going to fit an X, obviously train, Y, a target variable, epochs 100 meaning our model is going to look at the data 100 times, and batch size 32 is nothing but the sample size for each epoch. So while fitting the model, there's also another important variable called verbose. So verbose is nothing but the amount of information that your model should output. So if you specify 0, your model won't output any information, just the steps is going to output just the steps. If you specify 1 or 2, it's going to output the information like how many seconds are left, so how many batches are left to train. So this is not anything complicated. Just for reference purposes, you can play with verbose and all. And the next step is evaluating the model. So evaluating the model requires that you first choose a holdout data set used to evaluate the model. So we have already used train test grid, right? So we should evaluate the model and test validation data to be precise. Then we can make a prediction on the test data. This should be the data not used in the training process so that we can get unbiased estimates. So while evaluating, you should not supply the training data itself, because your model already trained on the training data, and hence evaluating it on the training data will be termed as cheating. Like, it will get biased, and since it already knows the data set, it doesn't perform better. So you can't really evaluate the model if it's doing good or not. And it's basic example, real life example is that you giving the students the question paper even before they write the exam. So they all get the question paper, and they all know what answers they're going to get. And next day when they write the exam, everyone is going to get good marks, obviously. So that will not be good evaluation metric. So hence, we should not train the model on the training data itself. The next step after evaluating the model, so you evaluated a model and you're happy with your results. The next step, you move on to predicting the data. For prediction, you can use test data. So making a prediction is the final step in the life cycle, and it is why we wanted the model in the first place. From an API perspective, you simply call a function to make a prediction of a class label. So in this case, it can be anything. Probably sigma. If you're using sigmoid, it can output a probability or softmax or anything. And you may want to save the model later and load it to make predictions. So saving a model is like the final step. I'll show you at last how we can save a model. And with this, our model life cycle is ended. So this is the basic structure that we're going to follow while building a neural network. So now we'll see how to add different layers to the particular model. So this is also a demo. This is how it's going to look like. Sequential models API is nothing but a simple syntax that we use to build neural networks upon. This example below defines a sequential MLP model that accepts 8 inputs, input shape 8, and has one hidden layer with 10 nodes. So inside the hidden layer itself, you can specify the input shape that the model is going to take. So that's what the advantage is with building sequential models. The syntax will be very easy to build an artificial neural network. So in this demo model, we have used like one input layer which has 8 features, 8 nodes, and a hidden layer which has 100 nodes, and another hidden layer which has 80 neurons, and another hidden layer which has 30 neurons. Like this, we have like 6 hidden layers and just one output layer, which is going to be like a sigmoid function, which is going to output just one variable. So this is the basics and the basic architecture of neural network, and how it's going to be performing upon your data. Implementation. Now let's look how we can really get the data and get the model really working. So I'm going to import the basic libraries that you'll be needing: TensorFlow, Matplotlib for plotting, and NumPy, obviously. And for this, I'll be using Kera's pre-built dataset, MNIST. MNIST is nothing but the digit dataset. I'll be using that. I'm loading it, and I splitted the data into training and test. So we have like about 60,000 images for extrain and 10,000 images for testing. And the shape of that particular image is going to be 28 by 28. This 28 by 28 is nothing but the pixel representation. So this is a 28 by 28 matrix which holds pixel values of that particular image. So this is how it's going to be looking like. This is 28 by 28 matrix, and you can really see the RGB values at each pixel. So this whole numerical matrix can be represented using an image, but by using Matplotlib's matShow function. So this is what this represents. So this matrix, you can see all these RGB values you can see corresponds to this particular image. So this image is represented in a mathematical matrix form above here. So we can clearly see this is a phi, and this also represents a phi. White range 0 also gives us the value phi, and we're going to normalize the data. Since you already know the highest amount of RGB value is 225. We'll be dividing each and every value by 255 to normalize the data, because the scale will naturally be between 0 to 25. So it's better to scale, because I've already told you the benefits of scaling. So that's what we're going to do. We're going to scale all the data by the size of RGB, the maximum size of RGB, which is going to be 255. And after scaling, our data will be like this, all scaled between 0 to 1. This is how it looks like. And after that, you can't supply a matrix to a neural network. You have to flatten it. Flatten it meaning you can't supply an image directly to a neural network. You have to create it according to the shape that neural network can understand. So that's what we're going to do right now. What we're going to do is that this image has 28 by 28 pixels, right? What we're going to do is multiply and flatten this image into a single dimension. So 28 into 28 gives us 784, and our model's input feature is going to have 784 variables, which is going to go into the neural networks. So as you can see clearly here, X-trained flattened, I have reshaped the training data into the number of training samples we have by 28 into 28, which is going to give us 784. And you can clearly see the shape, 60,000 records and 784 columns, so which is going to give us the features. So this representation is how this is really happening. So we have an image 2, and it is represented in this 28 by 28 grid. You can really see the RGB values here. And what we're doing is that we are flattening it out, 28 by 28 into 28, 784. So we are flattening out each and every pixel and creating it into a just one single dimension problem. So we can feed this entire data into the neural network. So you can clearly see that X1, X2, X3 are the features till we have X784. So we're going to have 784 neurons for the input shape. And these are all the output functions that will be using sigmoid activation function. Hence, there are 10 digits, right, from 0 to 9. We'll be using 10 output layers for this particular problem. And after training the neural network, that particular output variable which represents 2 is going to be high. The probability is going to be high. Like, or in this case, this value has 0.92 when you compare it to other values. So what it's going to do is that take argmax, not the max, argmax function. Argmax function is nothing but if you give a list in Python and take the argmax, it is going to return the index of the maximum function which is being located. So in this case, the index of this particular value which is being high is at 0, 1, 2. So it's going to return us the value 2, which is the answer for this particular image. So let's see how we can really build this model using basic artificial neural networks. As I said, I'm defining a model, artificial neural networks. We're going to be using Keras, sequential, the dense layers. We're going to be using no hidden layers, just one layer, one input layer and one output layer directly connected. And let's see what happens. Input shape 784, we have specified this is the 784 features, and we are directly connecting it to the 10 output neurons, this 10 variables, and we are going to be using activation sigmoid. We're going to be using sigmoid for the activation, hence it returns the probability. We're going to take the argmax of the value and return the output value. So for this particular problem, we'll be using Adam optimizer. Since I already told you it's the best option to go. Loss is sparse categorical for cross entropy. So hence we have a lot of different classes. This is a classification problem, right? This classification problem has 10 labels. Hence we will be using this particular problem. So whenever you have categorical classification, it's better to use sparse categorical cross entropy loss function. And the metrics we'll be using is accuracy. Now the next step, let's fit the model on the training data first. So we'll be plugging in the parameters, X-trained flattened layer. So this is the X-trained flattened we have here. The normalized data also, which is, and the wide range, and epochs we're going to set it for 5 epochs. Just we're going to keep it simple. 5 epochs is nothing but the model is going to look at the data 5 times. Now let's train. We get an accuracy of 92%. with training 5 epochs itself. And let's evaluate this model on the test set. On the test set also we get at around 92%. And let's predict these values. So after predicting for a particular for all the test data, and we'll store all the predicted value in this variable, and let's see for the first image what are the values a model like really output for the first image. So our first image is 7, right? You can clearly see it's a 7. Humans know, but let's see what our architecture predicted. So these are all the values. Probability, this is nothing but the probability. 1.53 is nothing but the probability. 7 is the probability. 5, 9, likewise. These are all the probabilities that model is outputting. And let's take the argmax. Argmax is nothing but finds the maximum element from an array and returns the index of it, like I said. So let's apply argmax to this y predicted, and when we get the results, it's 7. So hence is what my conclusion is, that a model predicted this image correctly. A model predicted this image as 7, which is right. And let's plot a confusion matrix. You might all know what confusion matrix is. It represents the correlation between the truth predicted and the truth and the predicted values. Exactly. We're gonna plot that. So we have a lot of accuracies. We have like high amount of accuracy. I said 92%, which is like slightly bad. If we can train for more epochs, the model is going to perform better naturally. But this is the confusion matrix. So out of all these actual zero values, our model predicted 0 958 times. So likewise, this follows. So what you can interpret from confusion matrix is that all the diagonal elements you can see here represents the correct values which are model predicted. So there are a lot of corrected values, and there are a lot of some errors you can see here. There are 32 incorrectly predicted values. So we can handle them later by increasing the number of epochs and cleaning the data. So since we get this kind of results because we didn't use hidden layers, now let's use hidden layer, because for the previous problem we just straightly connected the entire input shape to the output shape. So for this particular problem, in the next step we'll be using one hidden layer. So we already got a hidden layer with 100 neurons in it, and the input shape is obviously going to be 784, and the activation is going to be ReLU, and the dense is nothing but the output layer. We have 10 digits, hence 10 neurons, and the activation is going to be sigmoid. Next step, we will be compiling the model. As I said, optimizer Adam, loss, sparse, categorical cross entropy, and the metrics will be accuracy. We'll be using the exact same data and the exact same number of epochs. So you can clearly see the accuracy here is 98%. We have increased from 92 to 98% just by using one hidden layer and increasing the number of neurons each neural network holds. And this is the score we get on the test data set. Evaluation metric, we have used accuracy, hence we get the accuracy value, and on the test data we get 97%. So for this also, I'll be plotting the confusion matrix. So you can gain a lot of inference from plotting confusion matrix. You can clearly see that it has performed better, because earlier we saw like the values being 32, 16, 40, and all here and there. Now it has been reduced to one single digit values. So our model has performed great. And there's also another approach for this. If you are like confused on why should we specify the input shape right here while specifying the hidden layer also, there's another method which specifies the flatten, which is a function provided by Keras to flatten the entire input image into that particular feature that we want to get. So the input shape we have is 28 by 28. We have to specify that, and when we specify that, Keras will take care of flattening the entire image. And next step is the hidden layer. We have 100 neurons, which has activation value, and the 10 neurons for the output layer, 10 meaning the 10 digits we have. And we're going to be using sigmoid for getting the probability. Same amount of optimizers, the loss and metrics we'll be using. And epochs from 5, we'll be increasing it to 10. So let's see what happens. So our accuracy has been increased by 1%. So from 98, it got to 99%. And on test set, it is at 97.5%. So this is basic architecture neural network that we can perform, and I've used digit data set for performing this operation. So this is very basic. This is the basic architecture neural network, the architecture, and I've implemented the basic structure, and got the results. So any doubts you have, I need to clarify. This is a basic structure you need to follow for building a simple ANN.
One question on chat box, sir.
Okay, just a second. Dear sir, adding more number of layers may bring complexity. Yeah. Obviously, adding more number of layers obviously brings complexity. That's what you need to perform trial and error basis. First, add a lot of layers, see what you get, what results you get. So in this case, if you had 4 to 5 layers, you'll be getting a lot of overshooting problems. That is, your model is going to overfit. So if you feel like your model is overfitting, you can always reduce the neurons and the number of hidden layers. So what I would recommend is initially use just 2 or 3 hidden layers, and for each layer use ReLU activation functions. That should generalize, and you can get a better idea on what model you can build, how you can increase the model's performance. Okay, dear sir, adding the same questions. Was I clear? Did you understand? Okay, thanks. Thank you. Any other questions? Can I move on to the next phase? Hello, can I move on to the next phase? Is there any questions that you would like to clarify? Okay, I'll move on. So the next thing is convolution neural networks. So this whole thing represents the use of deep learning models. Why do we use deep learning models? Only for these purposes, convolution neural networks. So CNN are a type of neural networks which are used to classify images. CNN and RNNs are the basic and complex neural networks that we'll be using in building some of the problems, and I'll briefly explain to you what are those. So first, let me explain what convolution neural networks are and what it really does. So in mathematics, a convolution is a function which is applied over the output of another function. In our case, we'll consider applying a matrix multiplication across an image, and in deep learning, cross correlation is called convolution, although convolutional operation in math, the letter is the difference from correlation. Nothing but what I'm trying to say is here, the digits data set we used was in grayscale. We did not use any RGB function, so that pixel size was also very small, 28 by 28, no problem. A neural network can handle that. Even by using a small image, 28 by 28 pixels, our input feature size increased from what we really used to input, like 5 to 10 to 784. That's huge amount of features for a neural network to handle. So in real world examples, the image is not going to be like between 28 and 28. So for example, if you take a full HD picture, full HD is nothing but 920 pixels into 1080 pixels. So that image is going to have 920 into 1080 pixels. Let's assume this image has a full HD picture which consists of 920 into 1080 pixels, and obviously this is a color image. Hence we're going to have three layers, RGB channels to be precise. And if you multiply 1920 into 1080 into 3 is the RGB channels, our total number of features is going to be 6 million. So we can't really like enter 6 million values into the neural network model. So let's see how we can go and reduce this type of problems, and this is where deep learning can be really useful. So for basically how we can classify a koala, what convolutional neural network really sees while classifying a koala. So this is very basic representation in layman's terms. So it sees the koala size. So we're gonna have 5 features, obviously: eye, nose, ears, hands, and legs. We're gonna like specify 5 features. We want the neural network to find 5 features. Hence, we're gonna be using 5 filters. and each filter is going to be assigned to each of those features, and it is going to find this particular feature in that particular image. So first feature eye, it has like found out the eye part of this koala, and it is given here. So nose, likewise nose, ears, hands, and legs. After that, it's going to aggregate these three values into another one single value. So this eye, nose, and ears is going to compressed into just one value, which is going to be the head. And this hands and legs, if this koala image has hands and legs, then it represents that koala has the body. So the next step, if this image has koala's head and koala's body, we can answer the question, is this really koala or not? So this is what convolutional neural network is really going to do. So like I specified here, for this particular image, the pixels, the total number of input features is going to be like 6 million. So you can clearly see 6 lakhs 22,000, 62 lakhs 20,800. So that's a lot. You can't really specify this amount of features into a neural network. And this is basic representation how convolutional neural networks really work. We'll be using a filter to aggregate the values of each of those pixels. Now let's move on. What really is convolutional neural networks? It is really a special kind of multi-layer neural networks, and they are made up of neurons that have learnable weights and biases. Each neuron receives some input and performs a dot product and optionally flows it with a non-linearity. The whole network still expresses a single differentiable score function. So there are a lot of thought process going into convolutional neural networks. So you should really think before building a perfect convolutional neural networks. But fortunately, we have a lot of pre-built pre-trained models, which are like, these are the famous pre-built models or pre-trained models we have on the net: LearnNet, AlexNet, VJG, Google LearnNet. So Google LearnNet is being used by our Google cameras and Google Photos. So all our Google Photos use this particular pre-trained deep neural network. And ResNet is also another important and popular convolutional neural network architecture. So this is all like pre-trained and pre-built. You can readily use these type of architectures for your particular model. Now let's see what it really does, how like image is converted, and output layer, how it can really predict a particular image. So right now we have 30 pixels here. This image is 30 by 30 pixels, which is going to have 9,000 values. And what we have done here is that you can clearly see that there are 4 features for this input layer. 4 features meaning 4 neurons. What we have really done is that we have compressed this entire 30 by 30 pixels into a 2 by 2 pixel image. So the total value is going to be 4, and these 4 pixels is going to be represented as a feature, and we're going to feed this to the hidden layers and get the output function or the output layer and get the prediction. So the conversion between this 30 by 30 pixel image to a 2 by 2 pixel image is what convolution really does. So this is just the idea. For that, we'll be using a filter or a kernel. If you want 5 features to be predicted from this particular koala image, we'll be using 5 filters: eye, nose, ears, hands, and legs. So you can really see a 3 by 3 matrix. I'll zoom in a little bit. You can see a 3 by 3 matrix. What it's going to do is that this matrix is going to hold like a basic bias and weight, an active initial values. It's going to hold some initial numerical values, and what it does is that this values is like pulled upon this entire image, and it aggregates or finds that particular feature and highlights them. So for eyes, we have the it represented as here. Our convolutional neural network specified that koala's eyes are located right about here. Same thing for nose. Nose is here, so it's specified it to be here. Ears, it found out to be here. Hands, like both of them are on the right side, and legs down. So after that, as I said, it's going to aggregate this eye, nose, ears into one feature, head, which has three filters, and again we're going to reduce them by applying convolution to one particular value. So this one being the head is located obviously on the top, and body is located obviously in the below. So using these 2 values, we're going to identify whether is this koala or not. After this, we're going to flatten. This is the this is the output image. Our output image is going to be like this. Our pixel is going to be like this. After that, we'll flatten and apply it to the neural network. So this is the process. So stride. Next is the stride. So as I said, this filter is going across the entire image and taking the aggregate value of the pixel. So we need to specify strides. There are different types of strides. Stride controls how the filter convolves around the input volume. The filter convolves around the input volume by shifting 1 or 2 units at a time. So usually the stride is set between 1 to 2. Stride is normally set in a way so that the output volume is an integer and not a fraction. So think of this as the koala image. We have like 1, 2, 3, 4, 5, 6, 7. So 7 by 7, 1, 2, 3, 4, 5, 6, 7. Yeah, 7 by 7 input volume. And we're going to use 3 by 3 output volume. So this is going to be the filter. So think of this as the I filter. Each is going to have some values. And what we're going to do is that apply this 3 by 3 matrix to that particular image and multiply the values in this with that particular pixel. So higher pixel and higher value will highlight the feature even more. It's going to increase the value, and at the same time we're going to reduce the size of this particular image. So this is what is happening. So we have reduced the size of this from 7 by 7 to 3 by 3. So from 49 features, we have reduced to 9 features. So that's what convolution really does. Why do we do this convolution? To reduce the complexity and to specify the model, to like give the clarity to the model, and it takes some amount of time, not more than a lot of features, but the training will be a lot faster. That's what I'm trying to say. The training will be a lot faster if you like apply convolution to a big image and reduce the size of that image. So this is a 2 by 2 filter with stride 2. So this is a filter. So let's take a stride among these. So first stride, we're going to have 5, 1, 8, 2. Out of these 4 values, 8 has the highest value. 8 is the highest value. So we're going to output it here. And the next stride, we're going to move 2 steps. So that's what we are giving here. 2 by 2 filter with stride 2. Stride 2 meaning without going on to the next column, we'll be skipping one column and going to the alternative one. So the next filter is going to land upon here 3, 9, 4, 2. So out of this, 9 is the highest value. So we'll be outputting that into this matrix. And likewise, it's going to come down here since it's a filter with 2 strides. Out of this, 3 is the highest, is going to go there, and 2 is the highest, is going to go there. So we have reduced this particular image to a 2 by 2 image, which has all the important features of that particular image. And padding is nothing but we are adding extra layers above the image, so the filter doesn't really miss out the important features. Because for this koala image, if that koala was like slightly left or right of that image and we apply filter, our filter might easily miss the particular feature. So that's why in order to overcome this issue, we can add padding. Padding means increase the pixel size by filling it with null values. So 0, 0, 0, and this is going to become an image, and apply the filter to this particular image starting from this value. So 3 by 3 means this first 3 squares we're going to take into account, and this is going to continue. So by doing this method, there will be no loss of information and it will be safer also. So what happens when you apply 5 by 5 into 3 filters to a 32 by 32 into 3 input volume? This 3 is nothing but the RGB values, and we're going to apply 5 by 5 filter to a 32 by 32 matrix. So the output volume would be 28 into 28 into 3. So we've reduced from 32 by 32 to 28 by 28. So this is what really does. This is what convolution really does. It's going to reduce the size of the image and make our training time much faster. And another concept, pooling. So pooling is another important concept that you need to take into account. Pooling is nothing but after applying the filter and after getting the convolutionized image, we're going to further reduce the size of the image by taking the aggregate or taking the max value. So it can be anything. You can even take the mean of this particular stride and input the value, or you can take the max. So this is what pooling really does. It's a type of convolution, but in order to reduce the size, we'll use pooling. So this is how it's going to look like. There's an image, so you can clearly see this is a 9, and where the black black spots are our pixel is going to be 1. So this is for reference purposes. Just think of it like wherever there's 1, there's a black line, and all these black line represents and connected represents the sequence, which is going to be 9. And we'll convolutionize this image. So this image has 1, 2, 3, 4, 5. 5 by 1, 2, 3, 4, 5, 6, 7. So 5 by 7. So this image contains 5 by 7, meaning 35 pixels. We're going to reduce the size, trying to find the important features of that particular image. So let's apply a kernel 1, 1, 1, 1, 1, negative 1. So this could be any values. You can initialize any values. It could be like 2 or 3, anything. Our filter can be, the filter can contain any values, and we're going to use just one stride. A stride is going to contain just one of them, and we're going to like move upon each and every column. So first 3 by 3 goes around here. It gets the aggregate value negative 0.11, and we'll fill it here. And after this, it's going to move on to here and find the, input the maximum value, or get the aggregate 1, and it follows entirely upon this image, and it has reduced the size from 5 by 7 to 3 by 5. So it has reduced the pattern from 35 pixels to 15 pixels, and you can clearly see this 1 represents the loop pattern here. There's a loop above this 9, right? All lines have a loop, so our neural network has identified that loop pattern and represented it here. After applying the filter, these values can be a lot confusing, and all these other computations, all these numericals may be like a waste of time and a waste of space. So what we're going to be doing is that we're going to be applying activation function to this ReLU. What it's going to do is that ReLU mutes out or completely ignores the negative values and only keeps the positive values. It's going to get the max out of each of these variables. So negative 0.11, after applying activation, is going to be as 0, since ReLU is going to take the max values. So where and all we have negative values is going to be 0, and whenever we have positive value, it is going to be represented as the same. So 1 is represented as 1, 0.11, and 0.33. So after applying convolution and activation function, our image is going to be represented like this. But even still, we have a lot of zeros, which is a waste of space, and there's not really much information that we can get from this. So this is really a waste of space. So further, in order to overcome this issue, we'll apply pooling. Pooling is the same as applying the filter, but this time we're going to get the maximum value of each of the squares. So for the let's use the 2 by 2 matrix. First, it takes into account these 4 squares. We'll get the maximum value. It's going to be 1, and input it here. Another thing, 1, and it's going to do the same thing for everything. And it has reduced that image from a 3 by 5 image to a 2 by 4 image. So even further, from 35 pixels, we have reduced to 15 pixels. But after applying pooling, from 15 pixels, it has reduced to 2 into 4, 8 pixels. So this is what convolution really does. It really brings out the important features in an image and mutes out the entire unimportant features. So this is how it looks like in a mathematical form of visual representation. This is going to be an image 32 by 32 into 3 RGB channels. We're going to apply 6 filters. 6 filters meaning 6 different features. And after applying that, we're going to have a matrix like this. After convolutionizing it, we're going to have 28 by 28 and 6. And further, we'll max pool it. So after max pooling, we get 14 into 14 into 6 channels. So as you apply a lot of convolution and a lot of pooling, your channels or your feature is going to increase, but the total number of size is going to decrease. So applied again another convolutional, and another time we have applied pooling. So we've reduced the image from 32 by 32 into 3 to 5 by 5 into 16. And after that, after like pooling the entire image, we're going to flatten it and apply the neural network. So this is what's happening. This is another visual representation what's really happening. And for the koala, as I said, this is a koala image. Eyes, nose, ears, etc. It's going to have 5 features. We're going to apply convolution. Obviously, the image size is going to decrease, but the feature size is going to increase. After you apply pooling, the image size is going to decrease, as well as the features are going to be increased. And head and body, we have aggregated or even further reduced it into 2 features. So from pooling, we have reduced it to we applied convolution to the pooled image and got 2 features, head and body. and further we have reduced the size by applying pooling. So we have reduced this big of an image till this small of an image, and this image holds the entire important features that the neural network need in order to predict that a particular image has koala or not. Now let's see the implementation. So let's see the implementation of convolutional neural network. Before that, if you have any doubts in this theory part of CNN, you can really ask right now. Any doubts I should clarify for this theoretical part of CNN? It can be a little bit confusing, but this is how I can explain it right now. No doubts? I can proceed to the implementation. Let me check the chat box.
No questions, Shashank. You can proceed.
Okay, let me proceed. So let's see the implementation of CNN. So for this particular problem, we'll be using the same digits dataset. I'm going to import the important libraries, NumPy,
Sorry,
Matplotlib.
Shashank. I'm stopping you. There is a question from Prabha. What are the
Okay.
features we have to take for face using CNN?
No, the features you can specify what and all you need. So if you need like 6 or 7 features, you can specify the filters. But finding out the features, neural networks takes care of that. We can't really specify that. So we hope that neural networks finds those features accordingly. There's the number of filters and number of features that we really want. Is it clear? How to blur the image background, sir? Any filter for blurring? Blurring the image. So naturally, if you feed the image a blurred image, the blurred values are going to be decreased, are going to be ignored. So there's no really use to blurring the image. How to blur the image background? Oh, you want an image, a blurred image. You want to feed an image into the neural network and get the blurred background, right? That's what you're trying to say. Okay, so you're really asking the portrait mode from Apple, like that iPhone portrait mode of iPhone, and like the portrait mode, right? When it really focuses the subject and eliminates the background. So when you feed an image into the neural network, we can train it to identify the particular subject which we are interested in, and change the neural network into that particular architecture that it finds only the subject and mutes out the entire background or reduce the opacity. We have using blurred image in CNN. What will happen? No, if you use blurred image in CNN, nothing happens. It just mutes out the same thing and it follows the exact same steps that I have specified right now. If you provide an entirely blurred image, obviously a model is going to perform poorly. So as I said, poor quality of data is equal to poor quality of the model. Is it clear? So let's move on to the implementation part. I'll be importing NumPy, Matplotlib, and train, test bed, confusion matrix, all the basic libraries. And for this, I'll be using Keras, already specified. Let's import the Adam optimizer that we'll be going to be using. Learning rate schedule is nothing but a callback. I'll be explaining it in a few seconds. First, let's import the train file, test file, and the output file. And I'm loading the data, and I'm outputting it. So each data point consists of 784 values, which is nothing but 28 by 28 matrix, and a fully connected net just treats all these values the same, because our image is going to have 28 by 28 pixels. And this is the basic structure that we're going to be following. So this is number 9. So we're going to be including 1, 2, 3, 4, 5, 6 neurons. So each neuron is going to take care of that particular structure of that particular 9. So this neuron takes care of this particular a shade or a line, this particular type of this pattern, to be more precise. So this particular neuron, if an image has this particular pattern, it's going to classify it as 9. So likewise, it's going to split the network is going to split between the features that you want to put, and if this like you can really see this and this forms a loopy circular pattern. So this is like just exactly this type of paste pattern that Paul also follows: eyes, ears, and nose. So if a picture has eyes, nose, and ears, we can specify it as head. So likewise, for specifying number 9, if that particular image has all these type of patterns, it's going to specify a loop, and it's going to fire that particular neuron which holds the value 9. So this really goes on. This is how you can the neural network finds a number. And let's represent that particular image in RGB values. So this is going to be a scatter plot of that particular image flattened, so 794 pixels across the different RGB values for that particular image. It's going to look like this, and this is some number. It's all handwritten digits. Even I can't understand what number is this. So, but our neural network can identify what number they have written. Since it's handwritten digit, it can really differ between people. So that's why we are specifying or supplying handwritten digits to neural network so that we can easily classify the type of handwriting and the type of number that we are like really inputting. Now let's reshape this entire data set, which has 37,000 rows and 784 columns. I'm reshaping it into a type of shape that the neural network can understand. And the next step, as I did earlier in the ANN implementation, I'm normalizing the entire data, and I'm like changing it into categorical values. So labels were given as integers between 0 to 9. We need to convert these to one-hot encoding. You can do this step really if you want, or you can use just the label encoding is also enough. This is just an extra step that you can do. One-hot encoding is nothing but if the value is 9, at the ninth index, our model is going to specify 1. So this particular vector represents the number 9, because at the 9th element we have the value 1. So likewise, if this vector has 1 here, this is going to represent 1, because this represents 0 and 1, 2. The index represents all. The index starts from 0, so hence that particular index, whatever value is there, that's going to be represented as that particular image. Now let's train the model. So Keras offers 2 different ways of defining a network. We will be using sequential API as we did for all the above steps, and we're going to be adding just one layer at a time. The most important part are the convolution layers, convolution 2D, that we're going to be importing from Keras library, and we're going to be using 16 filters for this particular problem, for that particular image. So 16 filters meaning 16 features. We'll be trying to extract 16 features from that particular image, and we'll be applying all the max pooling and batch normalization algorithms to this particular problem. So first, let's define the sequential model and add a layer. So while adding the layer, I'm specifying the input shape. So this is already flattened, and I'm specifying the input shape, and I'm applying convolution to that particular image with 16 filters, and kernel size 3 by 3 is nothing but this particular matrix. You know this, wait. So this particular matrix, so this is the filter, and its size is 3 by 3, right? So we'll be specifying the filter size here, shape of the filter, 3 by 3. And for this, we'll be using activation function will loop. Input shape we have to specify because it has one channel. It is grayscale, right? Black and white. So naturally, it has just one channel and 28 by 28 pixels. And we will be applying batch normalization. It is nothing but this function is gonna standardize these values. If these values have like the difference between them is high, one will be having 127, another will be having like 3 or 2. It's better to normalize. I've already told you, because the value is going to be between 0 to 22, 25 also. So it's better to normalize these values. And again, after normalizing, we'll apply convolution again to the same image and apply batch normalization. And for that particular image, we'll be applying max pooling with strides 2 by 2. And dropout is nothing but for avoiding overfitting problems, we'll be using dropout. So dropout specifies, in this particular scenario, we have specified 0.25. So nothing but for the entire structure, we'll be dropping out 0.25% of the neurons. So it's like switching off the light of the neurons in that particular layers to avoid overfitting problem. And again we'll be applying convolution, and again convolution, and again max pooling. After you're satisfied that okay, I will be stopping with this, you can flatten the entire layer, and create the neural network. So this is a real neural network with 512 neurons and activation function ReLU, and another hidden layer with 1024 neurons with activation ReLU, and the final output layer is going to have 10 for the 10 digits, and activation is going to be softmax. Softmax is nothing but it returns the argmax value. So this is what is happening right now. Another important method to improve generalization is augmentation. You can also augment the data. I'll tell you how we can do that. But before, let's see the representation of what really is happening in this above layers. So when you input this value into convolutioning, when you convolutionize this image, it's going to be represented here, 16 filters, and after that you'll be applying max pooling. The size is going to get reduced, and for this max pool image, we're going to apply another convolution neural network, and for that we'll be applying pooling also. So after these 4 steps, we can flatten this and feed it to a fully connected neural network, and this output is going to be between 0 to 9, so 10 digits. So as I said, data augmentation is also a part. I'll be augmenting the data. Augmenting the data is nothing but when you have less number of images in your data set, like say if you have like only 500 images, augmentation can really help. What augmentation really is that we take an image and zoom it and create another image from that particular image. So we can shift the height, we can distort the image, we can completely rotate that image, and from one image, just from using these 4 parameters, we can generate 5 images just from one image. So that's going to increase our data set from 500 to somewhere between 2500. So we increase our data set from 500 to 2500. So the more data, the model is going to perform better. So that's the only reason for augmenting the data. And now let's compile the model we have created. This is the model architecture we have created. Now let's compile it. We have used categorical cross entropy as a loss function. Obviously this is a classification problem, and I've used Adam optimizer, and I've set the learning rate. Learning rate is nothing but the alpha value or the learning steps it's going to take in order to converge at the global minimum, which is going to be 0.001. Sorry. So 1e to the power -4 meaning 10 to the power -4. So another thing is that a learning rate scheduler. Keras provides this wonderful function of learning rate scheduler, meaning for each epoch, we're going to reduce the learning rate by a factor of 0.9. So that's what's happening. For after each epoch, a learning rate is going to get reduced. Now let's fit the model. Datagen.flow. So I'm fitting the model into small batches because we can't really provide this big of data set to the neural network model. So we split the data into 16 parts, and each part has 500 steps. That's what I did here. Steps per epoch 500, and epochs is equal to 40, meaning our model is going to take a look at the data set 40 times. Verbose is equal to 2 is the amount of information you need from the model. Printing out here. Validation data is nothing but the validation data we have imported, and callbacks is the learning rate scheduler that you want to reduce the learning rate for every epoch, right? We have specified that, and you should specify that callback into this particular parameter, and we'll store that into this history variable. So when we store this entire model and train that model and store those variables, this particular variable will be having the total account of loss, accuracy, validation loss, and validation accuracy. The important thing for doing this particular step is that later we can use this particular variable to plot the loss curves and accuracy curves. So now let's start the training for 40 epochs. So you can see the gradual decrease in loss and gradual increase in accuracy for each epoch. So right from 0.8766 at starting loss, we have converged at 0.509, and right from 0.7241 accuracy, that means 72% accuracy at the start of the first epoch, At the end, we have reached at about 98% accuracy. So this is what happens. Now we built the model and trained the model too. Now let's evaluate the model. We'll evaluate the model and the validation data set and find out the accuracy and the loss. This I have printed out. So this 0.3f meaning print out the first 3 decimal. So from the radix point is nothing but the decimal point. I want 3 values to be printed out. And we got the final loss and final accuracy. Loss is at 0.020 and accuracy is at 99.5%. Now let's plot the loss curve. So the blue line represents the training loss, and the red line represents the validation loss. So you can really see after 20-year epoch, our model really converged at the global minimum, and after that it was just adjusting the model. So our model performed very good in this instance. Our loss is very close to 0. Which means our errors are close to 0 or approximate none. We have 0 errors. And this is the accuracy curve. So right from 0, it has shot up to almost 100% accuracy. So red is the validation accuracy and blue is the training accuracy. Now let's get the predicted models. We'll predict the values for X validation and store it in this y hat variable. Y hat is nothing but the predicted values. And we'll plot the confusion matrix for this. So the diagonal elements represent the correct values. You can really see there's just 1 or 2 errors here and there. So meaning a model has performed really well for this particular problem. So hence, that's why we use convolutional neural networks. Not too bad, considering the minimal amount of training so far. We have only gone through the training data approximately 5 times. With proper training, we should get really good results. This is already good. If you want to increase the percentage even more, you can really increase the epochs or play with the data. So that's all for convolutional neural networks. Any doubts in the implementation part? Sir, okay. Sir, I have doubt. The number 9 is same as small g. How to differentiate? No, this is just classification problem. Like we're going to be outputting values between 0 and 9. If that particular number looks like a g, it's going to be outputted as 9. Our model is going to predict that particular image as 9. So that's why we supply this type of images to the neural network so that it can generalize better and predict better. This differentiation purposes, neural networks takes care of that. Not a problem. Can you use 3D convolutional filters? Yeah, you can use, but not this particular problem. This particular problem doesn't require that much of complexity. 2D convolution is more than enough because the image we are having right now is just 2D and which has 3 RGB channels. Using 3D convolutional neural networks, 3D convolutional filters also produce the same results as 2D convolution. So why the unnecessary complexity? So that's why we use 2D convolutional filters. It's going to produce the same results. But
sir?
Yeah.
Sir, suppose we are doing more max pooling and max convolution, what will be the result?
Your image is going to get completely compressed, so you have to do that with caution, right? You can understand my point. So you can't really do that again and again and expect the results to be great. It's like overfitting. You can't really compress the image from 28 by 28 to just 1 by 1 pixel. You need a lot of information. So that's why whenever we have to apply max pooling and convolution, you should be cautious and just stick on to some small initial filters. That's it. And later, if that particular result doesn't satisfy you, you can always increase the pooling layer and convolution filters. So this whole process is sort of trial and error. Nobody knows the perfect way to get the perfect results. So it really depends upon you. So any other doubts? Can I move on to the next topic, recurrent neural networks? Okay, I'm resuming. So before going to recurrent neural networks, please excuse me. I'll be having some water. So yeah, the next topic is going to be recurrent neural networks. So what really is a recurrent neural network? In a recurrent neural network, we store the output activations from one or more layers of the network and use that particular output to again train the model. So when we input new feature, our recurrent neural network is going to supply the weights and biases of the previously inputted feature to this particular image, or not image, but this particular feature set. So it's like remembering the past information. Recurrent neural networks, what it really does is that it uses the past information and supplies that particular information to the newly supplied feature, and it increases the accuracy of that particular model. So that's what I specified here. In a recurrent neural network, we store the output activations from one or more of the layers of the network, and these are the hidden layer activations. Then the next time when we feed an input example to the network, we include the previously stored outputs as additional inputs. So that's what is happening here. So consider HT as the output variable and X is the input feature. When we supply this input feature and after this neuron gets trained and applies the activation function, this particular neuron stores all the weights, and after the output variable, when you supply a new input feature, it's going to take the past information, that the past trained weights and biases, and supply that particular information to this particular input feature. So that's what is really happening in recurrent neural networks. So types of recurrent neural networks that we have is auto-completion. An example. So when you like in Gmail, when you type an email or like text message, then you type like not interested at, your auto-completion suggests this time, and if you type like will let you know if it changes in the future, it auto-completes, right? So this follows a sequential pattern. So that's why we use recurrent neural network. Artificial neural network doesn't really understand the sequence, but recurrent neural network understands some of the past information and uses that to predict the future. So that's why we use recurrent neural network. So this is one of the example, auto-completion which is available in your mobile and while typing Gmail also. And second is name entity recognition. When you supply a sentence like Rudolph Smith bought 1,000 shares of Tesla Incorporation in March 2020, when we supply this particular statement in a recurrent neural network, it identifies the person, the company, and time. So for all of this to happen, a neural network must remember the past information that we supply to the network. So this is where recurrent neural network comes in handy. Use cases. These are the type of use cases that we can use. So translation, Google Translation. When we like type "How are you?" and we need to like translate this particular English statement into Hindi, we can use recurrent neural network for this. So all the Google Translation algorithms uses recurrent neural networks. So in NER we see name entity recognition and sentiment analysis also. So just from this statement, as humans, we can really see that this is not a good statement. Hence, this statement really compares to a negative statement. Hence, the 1 star. So what recurrent neural network really sees is that not these words, the key words not broken, expensive. So it really identifies these words not expensive, broken, and all, and decides whether it is good or bad. So that's why we use recurrent neural networks instead of artificial neural networks. So yeah, why can't we use artificial neural network for sequence model, and how RRN handles this problem? So issue number 1, how are you? We need to translate this text into Hindi, right? Artificial neural network is constrained upon neurons. So it really cares about just one feature and represents another one feature. It really doesn't have the past information. And if you want to add like biryani, did you eat biryani? Artificial neural network can't really classify and doesn't know where to input that particular word into that particular sentence correctly. Too much computation. Yes, we can't really input this text messages into a neural network. So neural network can't understand string or text. We need to change these values into a value which neural network can understand. So how can be like represented into numerical value, like it can be one hot encoded, and the type that we'll be using in RRN is that there are a lot of words in the dictionary. So the dictionary is sequenced into alphabetical order, right? So this how word we can use the dictionary and find that, and we can get the index of that how word in the dictionary. So if the how word is H and it sits at about 600 or 1200 spot, we can use that entire features and input the value 1 at that particular index where how sits. So it's going to increase the computation is getting will get increased, and it's going to be too much of a work for neural network to unwrap this or unroll this entire words. Even for 3 words, it's going to be a lot of work. Imagine for like a complete paragraph or sentences or like an essay or that sort of stuff. So too much computation. That's where ANN suffers. And not only for the input feature, while outputting the values also, we need to one hot encode that particular feature. So it's like too much of computation. So that's why ANN really fails in classifying these type of problems. So the first is encoder and decoder. So for language translation, we will be using 2 of those things, encoder and decoder. Encoder is we're going to input the features from how are you, and the neural network is going to take care of those decoding. So the next thing, even though RRNs are quite powerful, they suffer from vanishing gradient problem. Like they can only remember 4 instances or 4 iterations of the particular problem. Like they are good for storing memory to 3 to 4 instances of past iterations, but larger number of instances don't provide good results. So we just don't use RRNs. So RRNs is a good RNNs are like good idea, but we can't really use them for this particular classification problem. So what we'll be using is LSTMs and GRU. So LSTMs and GRU are built on the basic idea of RNNs, and let's see how these 2 algorithms work. What is vanishing gradient problem? As I said, RRN suffers from this particular problem. Vanishing gradient problem is a difficulty found in training artificial neural networks with gradient-based learning methods. So decay, it represents the decay of information through time. So when you increase a lot of features and through time, our RRN doesn't remember the information it initially stored. So what it's going to do is that it's going to slowly decay and forget that particular information, leading to worse results. So that's what vanishing gradient problem is that. And let's see how we can tackle this particular problem using LSTM and GRU. So this is how we can represent an RRN. Today, due to my current job situation, family conditions, I need to take a loan. So that's a statement. So that's going to get categorized into this. So this whole architecture is nothing but just one hidden layer or one layer which is represented through time. So this whole statement is just one particular hidden layer, and I've represented it as a lot small subsets to like really get a sense for you to understand like what's really going on through time. So this is not like different types of hidden layers. There's just one layer, but I've represented each of those words in type of small subset cells. So that's what's happening. Now let's look at what LSTMs really do. So LSTM is nothing but long short-term networks. So that's where it comes in. So this is a short-term memory cell in traditional RRN. So RRN follows this type of networks. And let's see what really is said in LSTM. LSTM is a long short-term memory units or blocks are building unit for layers of recurrent neural network. So basically in layman's terms, what it really does is that LSTM figures out what information that it needs to keep and what information that it needs to discard. So that's what's really happening. RRN composed of LSTM units is often called as an LSTM network. A common LSTM unit is composed of a cell, an input gate, an output gate, and a forget gate. So the forget gate is the main step. So when you like see a particular feature and RRN decides to keep it, it will be in the input gate. And further into the sentence, if it sees another subject, what it really does is that it forgets this particular first subject and takes into the new subject input gate and stores in that value. So it records, LSTM basically records important information and discards the waste information. That the information the model doesn't need, it discards. Hence the word memory in LSTM. So this is the basic representation, what is really happening. So LSTM consists of 2 cells. One is the memory state cell from the traditional RRN. It is also going to use that and use that as input. And this is the cell state. Cell state is the main function of the LSTM, which controls or regulates the particular gates whether to forget or remember that particular feature. RRN completely takes care of this particular information, whether to discard that particular subject or to keep that particular feature in the cell state or not. So these are the components: forget gate, candidate layer, input, output, hidden state, memory state. Memory state is nothing but the state from the traditional RRN structure, and this is the basic structure of it. Let me explain more clearly. So there is this statement: Dawal eats samosa almost every day, and it should be hard to guess that his favorite cuisine is Indian. His brother Bhavin, however, is a lover of pasta and cheese. That means Bhavin's favorite cuisine is Italian. We need to find this cuisine, right? If Dawal eats samosa, samosa is obviously Indian cuisine. So we need to find this Indian cuisine and determine this. And after, let me walk through the steps what a LSTM does. So it takes the samosa word, stores that samosa word in its input or the memory cell, and after it finds this particular blank, it uses that samosa word and uses past information to identify it as Indian. But further into the sentence, when it sees the word pasta, it's gonna discard samosa and update the cell to pasta. Not even update, it's gonna input and forget samosa, but it doesn't really care about pasta. It's gonna go into the input gate, and later the output is gonna come like Italian, obviously. So this is what the structure looks like. We previously have samosa in this. So this is going to get into the activation function sigmoid, and as soon as it sees the input feature pasta, it's going to activate the forget gate. Forget gate has nothing but the value of the sigmoid function, which ranges between 0 and 1. So when it wants to forget samosa, it's going to activate the function 1, and when we multiply that into this weight c to the power t minus 1, our output value is going to be 0, meaning it has forgot that samosa is needed for that particular sentence. And the new feature pasta is fed into the input gate. For this, we'll use tan h activation function, and it's going to go into that, compute the activation function, and it's going to get updated in the memory cell, and we'll get the output as Italian. So this is what is happening in the structure of LSTM. Same thing. Now let's see the working. Working is nothing but the explanation that I gave right now. And now let's see the implementation of LSTM. So I will use LSTMs for predicting the price of stocks of IBM for from the year 2006 to 2017. So any doubts in the theory part of LSTM before continuing on to the implementation part? Any doubts I should clarify? No doubts, theory part of LSTM. So I'll be moving on to the implementation part. So as I said, we'll be predicting the IBM stocks for one particular year. This is going to be 2017. I'll be importing NumPy, Pandas, and Matplotlib. I'll be importing min-max scaler for this particular problem. The scaling is important, as I said yesterday, data preprocessing. Importing KRAS, sequential dense, LSTM, dropout regularization, GRU, and bidirectional. So we'll be not be needing GRU in bidirectional, but I imported these two features because in further sessions of this particular project, we'll be using GRU and bidirectional also. And the metrics I'll be importing is mean squared error. So the loss function is obviously going to be mean squared error. So this is a helper function I created to just plot. This function just plots the value that I supply in the test statement and the predicted statement, and it just compares the two output values and it plots them. So that's what it really does. And this is the loss function I have created. Nothing much. The root mean squared error. All of you know root mean squared errors. And I have imported the data, IBM data, which contains data from 2006 to 2017. Contains the stock prices, the open price, high price, the closing price for that day, low price, volume, and the name of the company, which is obviously IBM. I'll be importing that particular data, and let's see the shape of this particular data. This data has like 3020 records and 6 columns, and let's check the null, and let's check this data for null values. So we are having just two null values of this total data set. So that's not the problem. We're going to leave as it is. And let's split this data into training and test. So while splitting, for this particular sequential models, we can't really use sklearn's train test split method, because train test split methods from sklearn, what it really does is that it randomizes and randomly picks the sample from the data set. So it randomly picks sample. If you specify like I need 80% of training data from that particular data set, what it really does is that out of that whole data, it randomly takes 80% of the samples. So it doesn't follow any quite particular order. So, but for sequential prediction, so in order to predict the stock price in this problem for the year 2017, we need the past information for the last 10 years in sequential order. We can't really jumble the values between them, because periodical values is important in order to predict the stock prices for the year 2017 correctly. So that's what I did here. I split the data into train and test. So it's going to locate the year 2016 and get the column. So we're going to just predict the high value for this particular problem. We're going to get the high price. So that's what I did here. I split the training test for high price for the 2016. So our training data set is going to have all the data from 2006 to 2016 for the column high price, and test data is going to have the 2017 column, which has the high price too. So let's plot what it really looks like. So this is going to be a training set data from 2006. IBM stock price has been like this. This is scatter plot. So you can see the fluctuations, and right up till 2017 we have training, and after 2017 for the entire year we're going to be using for the test data for the prediction basically. Now obviously this all lies between some of those important values. We can scale this data, but scaling is not really actually needed for this particular data set, because all these values lie between 80 to 40 and between 50 to 80, I suppose. You can scale it. Scaling is always better, but you can also avoid in this particular circumstance. It is not compulsory for this particular problem. You can also scale. There is no wrong in that. So I've imported min-max scaler, and the feature range is going to be between 0 to 1. So all our data is going to be scaled between 0 and 1. I stored that in the variable, and I've applied fit transform method and fitted that entire data set into this particular scaler and got the variable scaled training data. So now what I've done here is that I've created two new samples, X-train and Y-train, and what I'm trying to do is that for one prediction we'll be using 60 past values or 60 past information, and a neural network is going to train on 60 features and output the future value of 1. So that's what I'm trying to do here. So what I'm trying to do, I'll explain more briefly. To output or get the stock price for 1 day, I'll be using the information for 60 days. So the past 60 days information is going to go into the neural network and is going to output just one variable or the one value, which is going to be the predicted value in the future. So that's what I did here. The range 60 to 2769, there's nothing but the rows, because when you subtract 60, you're going to get that value. So from 60 to 2769, I have split the data set, and I've applied for loop and got all the data scattered in them, and I reshaped it, X-train and Y-train, and the shape is going to look like this. So X-train is going to look like is going to have 2709 records with 60 columns and one particular rank. So 1 is nothing but that's where the information are going to go and get stored. So Y-train is obviously we're going to have just one label, so one column and 2709 rows. So now let's build the architecture for LSTM. I imported sequential and stored it in the variable. Now for adding LSTM, we can use this particular library from sklearn. From Keras. We can import LSTM from Keras and specify the units. Units nothing but the number of neurons. Return sequences is true. You should always specify this, because whenever you'll be using LSTM in that particular neural network, we should always return the sequences. This is a Boolean value, so you should be using true if ever you have LSTMs that particular next layer. So next layer we have an LSTM, so that's why we will be using true for this particular layer. Input shape we have to specify, and we'll be using dropout regularization to avoid overfitting problem. So another hidden layer with the same number of units, and we'll be specifying return sequences is equal to true because we will be using another layer containing of the same LSTM network. Hence, we'll set this bool value to true, and we need not to specify the input shape to be extended again, because once you specify the input shape, the recurrent neural network obviously recognizes and will take care of the shape and all sorts of the shaping mechanisms and all. Neural network will take care of that, but initially we have to specify the input shape. So for here, the same thing, another hidden layer, same amount of neurons, same Boolean value for return sequences because I've used LSTM for this particular layer, the next layer also, and same neurons for this layer also, but hence I will not use LSTM for this particular layer. You need not specify the return sequences Boolean. So by default it's going to be false. So I've left it by default, and I've applied dropout regularization for this also. And the final, our output layer is going to have just one neuron, which is going to predict just only one stock price value, considering the 60 input features or the 60 pass data of the data set. Now let's compile. After like adding all these layers, we'll compile the model using our RMS prop optimizer. It can be anything. You can use ADAM or ADAGRAD or RMS prop. I'm like performing trial and error, so I've used RMS prop. And for loss function, and I'll be using mean square error. And let's fit the model using the training data and the testing data. So first we'll fit the model using train data, X train and Y train. Epochs is equal to 35. 35 meaning it's going to look at the data 35 times, and batch size is equal to 32. So it's going to split the data into 32 and send each batch into that particular neural network and get the output. So we really use batch size to like reduce the complexity, because we can't really specify or input these big values of numericals into this particular neural network. So that's why we split them into small chunks, that is batch size, and we train the neural network accordingly. So this ran for 35 epochs. You can clearly see. So naturally the verbose is going to be 1. I haven't like explicitly specified the verbose number, so but by default it's going to be 1. So that's why I've just got the value for just one loss. So for one value loss. So we have reduced the loss value from 0.0226 till 0.0019. So we have reduced the loss comparatively high. And now let's check our data set. Hence I did the same thing for training data. I have to do the same thing for test data also. Likewise, I did the same thing for training data. I have to follow the same steps. I should scale the data for test set, and I should do the same thing and should get the prediction for the same thing I have applied for training data also. Now I did the same exact steps, nothing fancy going on here. Now let's get the prediction. We have like specified the classifier to be regressor, and we'll be using that regressor.predict the test data. So the scale the test data, because we have scaled it using min-max scaler, right? We can't really use that model which is trained on scale data to get predictions on the normal data set. So hence we should scale the values. We should scale the test data values also, and we'll be using that particular set for prediction. After getting the prediction, we'll like inverse transform that. So what it really does is that this is a scalar we imported, and when we apply inverse transform, it inverses that scale transformation. So when we like scale the data for like example, let's say from 25 to 2, what inverse transform does is that from 2 it scales back to 25, giving us the actual price. So let's plot the predictions. So this is the predictions. So the red line is the real values, and blue line is the predicted values which are model predicted. And it is really, really good because you can really see the oscillations and the peaks are already fitted, and it's close to the red line, and our accuracy is high. So this is why we really use LSTMs in this particular scenario. So evaluate this. Let's evaluate this. We'll evaluate this particular model using root mean square error, and the error is 2.3, significantly low. We can also even reduce this particular error percentage even more by adding even more neurons, even more layers, and tweaking some of the stuff. But this is the basic LSTM implementation. Any doubts you have, I can clarify regarding LSTM. Any doubts regarding implementation and theory part of LSTM before moving on to data recurrent neural networks?
We can move on.
Okay, ma'am. Okay. Okay, the next important topic or the next type of implementation that we'll be looking is the gated recurrent units. So LSTM is not the only kind of unit that has taken the world of deep learning by storm. We have gate and recurrent neural networks also. It is also sometimes it is better than LSTM, sometimes LSTM is better than GRU. So it is more like trial and error. So some sort of problem or different type of problems yield better results if you use LSTM or GRU algorithm. So it's really trial and error. This one particular algorithm can perform better for one particular problem, and another particular the GRU can perform better than LSTM for one particular problem. So it really is a trade-off between them. So what really is a GRU? In simple words, the GRU unit does not have to use a memory unit to control the flow of information like LSTM unit, because LSTM unit has a short-term memory of the traditional RRN and the long-term memory cell state, which combines these. It has these two cells, but GRU combines these both into one single entity, long and short-term memory. That's what GRU does. It is almost similar to LSTM, but only the gates will be there will be difference in the gates, where LSTM has gate input output and reset input output gates, where GRU has just two gates, which will be update and reset gate. So this is the basic structure for GRU. This is our input feature. This is our previous cell state, and deciding on the factor of that particular sentence or of that particular information, our GRU is gonna decide whether it should be update the gate or reset the gate, or just keep the gate and move on to the next particular information. So that's what's happening in GRU. GRUs have very few parameters and thus may train a bit faster or need less data to generalize. But when you have large data, LSTM performs way better than GRU. So this is the basic architecture between these two, LSTM and GRU difference. It has a forget gate, has another cell state, input gate and output gate, but GRU has just two gates, reset gate and update gate. So these are the type of activation functions that is widely used in GRU and LSTM, sigmoid and tanh. Now let's see what really happens when you feed in a feature and feed on the cost information or cost weights and biases to that particular information. Our GRU decides to whether update the gate or reset the gate, and regarding to that particular gate which it chooses is going to get multiplied by the activation function, the tanh we have specified here, and uses all of this information into the output gate, and we can get the predicted value. So that's what really happens. Now let's see how to build a GRU model. So this is how you can build GRU. Keras also provides the same library. So Keras is the library that can provide you GRU. And I have used GRU from Keras, obviously. And let's build it. I've built this regressor. I built the sequential module regressor GRU, and I'm adding layers to that particular variable. I'm adding GRU unit, which is going to have 15 neurons. Return sequences is equal to true because the next layer we're going to be using GRU. Hence, you should return the sequences. Input shape we should specify, and we can specify the activation function tanh and add dropout regularization for this. I'm going to add another GRU layer with the same input. I have explicitly specified this shape, but you need not do that because neural networks does that for you. And I've added another neural network too, another hidden layer to be precise, with the same amount of neurons, same amount of dropout regularization, with another GRU with 50 neurons. But this time I haven't used return sequences because I've straight away connected this to the output layer using the activation tanh. So this output layer is going to have just one unit because we're going to predict the stock price of just one variable. Hence, one neuron is enough. And for this particular problem, we'll use stochastic gradient descent to be our optimizer, which holds the learning rate 0.01, and decay is nothing but the amount of the steps that it's going to take for each epoch, and the momentum is going to be 0.9, the speed. And the next drop is the basic parameter that we'll be using. Nothing fancy. Next drop is not needed right now. It's beyond the scope of this particular session. But that's the default parameter. Then loss is equal to mean squared error. Now let's fit this particular data set into the GRU architecture. And I've used the same number of epochs, and I've increased the batch sizes to be 150. So let's see the loss function for this. So right from 0.1315, our loss is reduced to 0.0023. It's a significant decrease in loss. And let's see the prediction for this particular architecture, neural network architecture that we built. So we got the predictions. I did the same thing. I followed the same steps that I followed for LSTM also for the test set, and I'm following the same exact steps for this particular GRU also. And I got the prediction for the test set, and since I used the same scaler for this also, I am inversely transforming those values to the original values, to the corresponding original values to be precise. And let's plot the predictions. So this is the red line is the original stock price, where the blue line is the predicted value, predicted stock price. So the root mean squared, our evaluation metric, root mean squared returned 3.308. So compared to this 3.308 to its LSTM's 2.2, I suppose. Yeah, 2.36. For this particular problem, LSTM's error was less than GRU's error. So for this particular problem, LSTM performed better than GRU in this case. Yeah, but this may vary for different data sets. Applying both LSTM and GRU together can also yield better results. So this is like trial and error. For this particular problem, LSTM obviously performed better, but another problem, GRU might perform better. So there is a trade-off between these two algorithms. You can always try these both algorithms and use whatever is good for you and whatever yields the better results. So the difference between LSTM and GRU, the main differences are LSTM holds 3 gates, input, output for get. GRU holds only 2 gates, reset and update. It is fairly easy. It is less complex. GRU is much faster than LSTM. But when you have a large data set, LSTM might be the better option for you. LSTM is more accurate and longer sequence. That's what I said. GRU is more computation efficient and is getting popular. LSTM was invented in the year between 1995 to 1997, whereas GRU was a recent development. It was just invented like 6 years ago. And after all this, after you build a model, how can you save and load it? So Keras also provides the save function where you can save that particular model into a file which represents H5, and model is saved in H5 format, an efficient array storage format, and you can ensure that the H5 library is installed on your workstation. So when you install Keras, H5 format also installs simultaneously, and you can use this to save your model. So what it really does is that this H5 extension really stores the weights and updated weights and updated biases and the estimators of your created model. And later you can load the same model or your saved model from this load model function provided by Keras, and you can load this model from this particular syntax. You can import the load model and tell that particular file or name that particular file and load it into this variable. So our model is stored in this particular variable. So that's it for today's session. Any doubts in GRU I need to clarify? And like theory part and like in implementation part, any doubts you have? Check. Let me check the chat box.
There's one question from Mr. Barnier. Please explain about vanilla LSTM.
Okay, vanilla LSTM is which holds just single hidden layer of LSTM units. So vanilla is nothing but plain, right? Vanilla is a plain ice cream. So like that, vanilla LSTM is a plain LSTM network which holds only one hidden layer. So that's it. Vanilla LSTM is nothing but a neural network which holds only one single hidden layer consisting of LSTM units. That's it. Any other doubts? I actually thought of showing you two projects which I did on neural networks, but time did not permit. For explaining theoretical implementation part itself, we thought like time was not available, so no problem.
We can even extend one more session. Thank you, Shashank.
Okay, thank you, ma'am. Thank you, ma'am.
Thank you.
Any doubts?
It's
I was.
really interesting.
Thank you
And
so much.
I think if time permits, we can even extend one more session.
Yeah, if time permits.
Yeah. Okay, Shashank. It was really nice of you for delivering for the past 2 days.
Okay,
And
thank you so much. It's my honor.
hope the participants would have benefited from this sessions.
Yeah, sure.
I think it was a positive feedback yesterday. Today, uh, they were able to clear all their doubts. They interacted also well.
Yeah.
And thank you, participants. And tomorrow would be the last day of the event, 5-day FDP. And being Saturday, I hope everyone will join the session. And we also have a hands-on session by using open power systems from IBM. So I request everyone to join tomorrow's session and utilize the opportunity.
Madam, feedback not accepting the responses, madam. Please send the new link, madam. Please.
Yes, sir.
Thank
Yes,
you.
sir.
Thank you so much,
Yeah, yeah.
madam.
Sandhya ma'am.
Second, ma'am, I'm checking this feedback form. 1 second.
Okay, ma'am. Participants, please wait. The feedback form will be posted again.
Sorry for the inconvenience. Now feedback form is working. So please fill the same. Thank you.